Imagine buildings that literally breathe, heal themselves, and even grow over time. What if your home could automatically repair its own cracks, purify polluted air, or regulate temperature like a living organism? Sounds like science fiction, yet this future is already under construction. Today, engineers and architects are blurring the line between biology and infrastructure. Welcome to the revolutionary world of bio-integrated architecture, where buildings are no longer passive concrete shells, but living systems designed to interact with nature. In this video, we'll explore how living organisms, self-healing materials, and bioresponsive systems are redefining sustainability and pushing civil engineering into a new era. Get ready to rethink everything you thought you knew about buildings. Welcome to Civil Engineering Edge, the channel where cutting-edge engineering meets the future of the built environment. If you are a civil engineering student, a practicing professional, or someone passionate about sustainable infrastructure, this video is designed for you. Traditional construction has shaped modern civilization, but it has also strained our planet's ecosystems. Today, engineers face a critical challenge, designing structures that do not merely reduce harm, but actively restore environmental balance. In this episode, we dive deep into living buildings and bio-integrated architecture, an emerging field that merges civil engineering, material science, and biology. From self-healing concrete to photosynthetic façades, we'll explore how buildings can become adaptive, regenerative systems. This is not just architecture, it's the future of engineering itself. Imagine buildings that literally breathe. Imagine a building that behaves not as a sealed concrete box, but as a living, responsive organism, one that continuously exchanges air, energy, and moisture with its surroundings. In bio-integrated architecture, the idea of buildings that breathe is rooted in real engineering systems inspired by biological respiration and transpiration. These structures are designed to regulate indoor environments naturally while improving the external ecosystem. Breathing buildings often incorporate living façades, algae bioreactors, and porous biomaterials that enable controlled air exchange. One of the most advanced applications is the use of algae-filled façade panels, where microalgae absorb carbon dioxide and sunlight to perform photosynthesis. From a civil engineering standpoint, this process produces multiple benefits simultaneously: carbon capture, renewable biomass generation, solar shading, and reduction in internal heat gain. As a result, the building's reliance on conventional systems is significantly reduced. Another key element of breathing buildings is bioresponsive envelopes. These are façade systems designed with hygroscopic or bio-based materials that expand or contract based on humidity and temperature changes. Inspired by plant stomata, these envelopes open when ventilation is needed and close when conditions are harsh without motors, sensors, or external power. This passive adaptability represents a major shift from mechanical dependency to material intelligence. In polluted urban environments, breathing buildings act as environmental filters. Living walls made from mosses, lichens, and microbial layers trap particulate matter, absorb nitrogen oxides, and improve air quality around dense city corridors. For civil engineers, this transforms buildings into decentralized air purification infrastructure. Ultimately, breathing buildings challenge the traditional definition of a structure. They are no longer static shelters, but active environmental systems that continuously interact with nature. This concept pushes civil engineering toward designs that prioritize adaptability, resilience, and long-term ecological balance. Beyond green, why current sustainable buildings fall short? Over the past few decades, sustainable or green buildings have played an important role in reducing energy consumption and minimizing environmental damage. However, despite these advancements, most green buildings remain fundamentally passive systems. They focus on efficiency using less energy, less water, and fewer resources rather than actively contributing to environmental restoration. This limitation has become increasingly evident as climate challenges intensify. From a civil engineering perspective, many sustainable buildings rely heavily on add-on technologies such as solar panels, insulation upgrades, and energy-efficient equipment. While these measures reduce operational emissions, they do not address deeper systemic issues like material degradation, embodied carbon, or long-term infrastructure resilience. Concrete still cracks, steel still corrodes, and façades still deteriorate, requiring frequent repairs and resource-intensive maintenance. Bio-integrated architecture goes beyond efficiency by embedding living systems directly into construction materials. A prime example is self-healing concrete, which contains dormant bacteria that activate when cracks form. When exposed to moisture and oxygen, these bacteria produce calcium carbonate, naturally sealing cracks before they grow into structural defects. For engineers, this significantly extends service life and reduces life cycle costs. Another shortcoming of conventional green buildings is their isolation from surrounding ecosystems. They may consume fewer resources, but they rarely enhance biodiversity or improve environmental quality. Bio-integrated buildings, in contrast, are designed to coexist and co-evolve with their environment, supporting plant life, managing stormwater naturally, and improving microclimates. In essence, green buildings aim to do less harm. Living buildings aim to do more good. This shift from sustainability to regeneration marks a critical evolution in civil engineering, redefining how infrastructure contributes to planetary health. A glimpse into the future, bio-integrated cities, and living infrastructure. The future of urban development lies not in smarter machines alone, but in living, adaptive infrastructure that evolves alongside its environment. Bio-integrated architecture offers a vision of cities where buildings function as interconnected ecosystems rather than isolated structures. In these cities, infrastructure is capable of sensing, responding, and even healing itself over time. Imagine urban skylines where façades photosynthesize like forests, absorbing carbon dioxide while generating energy. Roads and bridges embedded with self-healing materials automatically repair microcracks, preventing premature failure and improving safety. Buildings respond dynamically to temperature, humidity, and pollution levels, adjusting ventilation, shading, and moisture control without human intervention. For civil engineers, this future demands a multidisciplinary approach. Structural design will integrate biology, material science, and data-driven monitoring systems. Sensors embedded in living materials will continuously track stress, strain, and environmental conditions, enabling predictive maintenance and real-time performance optimization. Bio-integrated cities also promise enhanced resilience against climate extremes. Living roofs reduce urban heat island effects, bio-based drainage systems manage floodwaters naturally, and adaptive façades improve energy efficiency during extreme weather events. These systems reduce dependency on centralized infrastructure, making cities more robust and flexible. As research advances and pilot projects scale up, bio-integrated architecture will move from experimental innovation to mainstream practice. Engineers who embrace this paradigm today will shape the cities of tomorrow. Living buildings are not just the future of architecture, they represent the next evolutionary step in civil engineering, where infrastructure becomes a living partner in healing the planet. Nature's blueprints, from algae to self-healing concrete. Nature has spent billions of years optimizing structures for strength, efficiency, and resilience. Bio-integrated architecture draws directly from these natural systems, translating biological intelligence into engineering solutions. Instead of forcing buildings to resist environmental forces, engineers are now learning how to collaborate with natural processes. This approach forms the foundation of bio-integrated design, where living organisms and biologically inspired materials are embedded into the built environment. From a civil engineering perspective, this represents a shift from inert construction materials to adaptive, performance-driven systems. Algae, fungi, bacteria, and microbial colonies are no longer viewed as threats to buildings, but as functional components. These organisms perform tasks such as energy generation, insulation, carbon sequestration, and structural self-repair tasks that traditionally required complex mechanical systems. Nature's blueprints emphasize efficiency through simplicity. Biological systems operate with minimal energy input, self-regulate under changing conditions, and repair damage autonomously. Translating these principles into construction materials allows engineers to reduce maintenance demands, extend structural lifespan, and dramatically lower environmental impact. For students and professionals alike, understanding these biological mechanisms is becoming as important as mastering concrete mix design or structural analysis. As codes evolve and sustainability targets tighten, bio-integrated materials will move from experimental prototypes to standard engineering practice. This section explores 3 of the most promising innovations, inspired directly by nature: photosynthesizing façades, mycelium-based construction, and bioreceptive self-healing concrete, each redefining what buildings can do. Photosynthesizing façades, turning building skins into energy factories. Photosynthesizing façades represent one of the most revolutionary applications of bio-integrated architecture. These systems use microalgae bioreactors embedded within building envelopes to convert sunlight and carbon dioxide into usable energy. Unlike traditional solar panels that merely convert sunlight into electricity, algae façades perform multiple functions simultaneously, making them uniquely valuable from an engineering standpoint. In these systems, transparent or semi-transparent panels are filled with water and microalgae cultures. When exposed to sunlight, the algae undergo photosynthesis, absorbing CO and producing biomass. This biomass can later be harvested and converted into biofuel or thermal energy. At the same time, the dense algae layer provides dynamic solar shading, reducing heat gain and lowering cooling loads inside the building. From a civil engineering perspective, these façades act as climate-responsive envelopes. As algae density increases in strong sunlight, shading increases automatically. During low light conditions, the panels become more transparent, allowing natural daylight to penetrate. This passive regulation significantly reduces reliance on mechanical and artificial lighting systems. Structurally, algae façades must be carefully engineered to handle fluid loads, pressure variations, and long-term durability. Engineers must account for panel weight, anchoring systems, maintenance access, and integration with structural frames. Despite these challenges, real-world pilot projects have demonstrated long-term feasibility and energy efficiency gains. Beyond energy production, photosynthesizing façades actively contribute to carbon sequestration, transforming buildings into environmental assets. For dense urban areas struggling with pollution and energy demand, these façades offer a scalable solution, turning city skylines into living power plants. Mycelium as a building block, fungal networks in construction. Mycelium, the root-like network of fungi, has emerged as a surprising yet powerful building material in bio-integrated architecture. In nature, mycelium forms dense, interconnected networks capable of binding soil, decomposing organic matter, and creating structurally resilient systems. Engineers are now harnessing these properties to develop lightweight, sustainable construction materials. Mycelium-based materials are grown by combining fungal spores with agricultural waste such as straw or sawdust. As the fungi grow, they bind the organic matter together, forming a solid mass. Once growth is complete, the material is heat-treated to halt biological activity, creating a stable, non-living composite suitable for construction. From a civil engineering standpoint, mycelium offers exceptional thermal insulation, fire resistance, and acoustic performance. Its low density makes it ideal for non-load-bearing walls, insulation panels, and interior partitions. Unlike traditional insulation materials, mycelium is fully biodegradable and requires minimal energy to produce. Structurally, while mycelium cannot replace reinforced concrete or steel in primary load-bearing systems, it plays a crucial role in hybrid construction models. Combined with timber or light steel framing, mycelium components significantly reduce embodied carbon and improve indoor environmental quality. Additionally, mycelium materials regulate humidity naturally and resist mold growth, improving occupant comfort. For civil engineers focused on sustainable design, mycelium demonstrates how biological systems can replace energy-intensive industrial processes without compromising performance. Bioreceptive concrete, materials that heal themselves. Concrete is the backbone of modern infrastructure, but it is also prone to cracking, which leads to durability issues and costly maintenance. Bioreceptive or self-healing concrete addresses this challenge by integrating biological repair mechanisms directly into the material. This innovative concrete contains dormant bacteria, often from the Bacillus family, along with nutrients such as calcium lactate. Under normal conditions, the bacteria remain inactive. When cracks form and water enters, the bacteria become active and produce calcium carbonate, which fills and seals the cracks naturally. From a civil engineering perspective, this process prevents microcracks from expanding into structural failures. By sealing cracks early, self-healing concrete protects embedded reinforcement from corrosion, significantly extending service life. This is particularly valuable in bridges, tunnels, marine structures, and foundations exposed to harsh environments. Bioreceptive concrete also supports controlled biological growth on surfaces, allowing mosses or microorganisms to colonize the material without compromising strength. This enhances aesthetic appeal while contributing to air purification and urban cooling. While initial costs are higher than conventional concrete, life cycle cost analysis shows substantial savings due to reduced repairs and extended durability. As standards evolve, self-healing concrete is expected to become a mainstream material in resilient infrastructure design. Engineering the impossible, designing for life. For centuries, civil engineering has been defined by the mastery of inert materials: stone, steel, concrete, and asphalt. These materials are strong, predictable, and reliable, but fundamentally lifeless. Bio-integrated architecture challenges this tradition by asking a radical question: what if buildings were designed to host life rather than resist it? Engineering the impossible means creating structures that can grow, adapt, and repair themselves while maintaining structural safety and performance. Designing for life introduces unprecedented complexity into engineering practice. Living systems are dynamic, non-linear, and responsive to environmental stimuli. Unlike conventional materials with fixed properties, biological components evolve over time. This requires civil engineers to rethink design methodologies, safety factors, and maintenance strategies. Structural design is no longer based solely on static loads and material strengths, but also on biological behavior, growth cycles, and environmental feedback. This paradigm shift is supported by advances in synthetic biology, material science, robotics, and computational modeling. Engineers can now predict how microbial colonies will behave under stress, how smart materials respond to temperature and humidity, and how automated systems can place living components with extreme precision. Together, these technologies make it possible to design buildings that are alive in function, though controlled in performance. Engineering living systems does not replace traditional engineering principles, it expands them. Codes, standards, and testing protocols are beginning to evolve to accommodate bioresponsive materials. As this field matures, engineers capable of integrating life into structures will be at the forefront of resilient, regenerative infrastructure development. Microbial architecture. engineering bacteria to produce materials on demand. Microbial architecture represents one of the most groundbreaking intersections of civil engineering and synthetic biology. Instead of manufacturing materials in factories and transporting them to construction sites, this approach explores how engineered bacteria can produce building materials directly within structures, on demand, and in response to environmental conditions. Certain bacteria naturally produce minerals as part of their metabolic processes. Engineers are now genetically programming these microorganisms to enhance and control these behaviors. For example, bacteria can be designed to precipitate calcium carbonate, silica, or biopolymers when activated by moisture, stress, or chemical signals. In practice, this means a wall or foundation could strengthen itself over time or repair internal damage without human intervention. From an engineering perspective, microbial material production offers enormous advantages. Cracks, voids, or weak zones within concrete can trigger microbial activity, initiating material deposition exactly where it is needed. This localized response reduces material waste and prevents small defects from developing into structural failures. In underground structures and remote infrastructure, such autonomous repair capabilities are particularly valuable. Microbial architecture also enables in situ manufacturing. Instead of casting large components off-site, materials can be grown within formwork or porous scaffolds. This reduces transportation emissions and allows construction in challenging environments such as disaster zones or extraterrestrial habitats. Safety and control are critical considerations. Engineered microbes are designed to remain dormant unless specific conditions are met and are deactivated once their function is complete. For civil engineers, this ensures predictable performance and regulatory compliance. Microbial architecture redefines construction as a biological process, positioning engineers not only as builders, but as designers of living material systems. Adaptive skins, smart polymers, and biological sensors in building envelopes. The building envelope is the primary interface between a structure and its environment. Adaptive skins transform this interface into an intelligent, responsive system capable of reacting to changing climate conditions in real time. Unlike conventional façades that rely on mechanical systems, adaptive skins use smart polymers, biological sensors, and bio-inspired mechanisms to regulate building performance autonomously. Smart polymers can change shape, transparency, or permeability when exposed to heat, moisture, or light. For example, thermoresponsive polymers expand under high temperatures to provide shading and contract in cooler conditions to maximize solar gain. Hygro-responsive materials react to humidity, opening microvents to enhance ventilation during high moisture conditions. Biological sensors, inspired by plant and animal systems, detect environmental changes such as air quality, UV radiation, or temperature fluctuations. These sensors trigger material responses without external energy input, allowing buildings to sense and react much like living organisms. From a civil engineering standpoint, adaptive skins reduce reliance on fixed systems, improve energy efficiency, and enhance occupant comfort. Structurally, these systems must be designed to withstand wind loads, thermal expansion, and long-term fatigue while maintaining biological functionality. Adaptive skins also improve building resilience. During heat waves, they reduce thermal stress. During storms, they adjust permeability to protect interior spaces. This adaptability is critical for climate-resilient infrastructure in rapidly changing environments. By merging material science with biological intelligence, adaptive skins transform façades from static barriers into active climate moderators, marking a significant evolution in building design. Robotic construction with living elements. Automation meets biology. The integration of robotics into construction has already improved precision, safety, and efficiency. When combined with bio-integrated materials, robotics enables the controlled placement and cultivation of living elements within structures, something impossible with traditional construction methods. Robotic systems equipped with sensors and AI algorithms can place living materials such as bioconcrete, algae panels, or mycelium components with millimeter accuracy. These systems monitor environmental conditions, temperature, humidity, and light to ensure optimal growth and performance of biological components during and after installation. In 3D printing, robotic arms can extrude bioreceptive materials layer by layer, embedding microbial capsules or organic fibers exactly where needed. This allows for customized structural behavior, such as reinforced healing zones or climate-responsive surfaces. Automation also enhances safety when working with living systems. Robots can operate in hazardous environments, maintain sterile conditions, and manage biological materials without exposing workers to risk. This precision ensures consistent quality and scalability. For civil engineers, robotic bioconstruction represents the future of complex infrastructure delivery. It allows large-scale implementation of living systems while maintaining strict engineering control. The marriage of robotics and biology transforms construction sites into precision laboratories, where life and structure are built simultaneously. Case studies and early adopters, where it's happening now. Bio-integrated architecture is no longer confined to research papers or futuristic concepts. Across the world, universities, research institutes, and forward-thinking developers are actively testing living building technologies at real scale. These early adopters play a critical role in transforming experimental ideas into viable engineering solutions. By monitoring performance, durability, cost, and user response, these projects provide essential data that informs future design standards and construction practices. For civil engineers, case studies serve as proof that bio-integrated systems can meet structural, environmental, and safety requirements simultaneously. These early projects often operate as living laboratories, where façades, materials, and structural systems are continuously monitored and optimized. Data collected from these buildings helps engineers refine material compositions, improve design methods, and validate long-term performance assumptions. Importantly, early adopters are not limited to one region or building type. Bio-integrated technologies are being tested in academic campuses, office buildings, housing prototypes, and urban infrastructure projects across Europe, Asia, and North America. These real-world implementations demonstrate that living buildings are adaptable to different climates, regulatory environments, and construction cultures. While many of these projects remain experimental, their successes are reshaping how governments, investors, and engineers perceive the future of sustainable infrastructure. Case studies bridge the gap between theory and practice, proving that bio-integrated architecture is not only feasible, but increasingly necessary for resilient urban development. Pilot projects worldwide. Real-world experiments in living architecture. Pilot projects are the backbone of innovation in bio-integrated architecture. Universities and research institutions have been among the earliest adopters, using experimental buildings to test living systems under controlled yet realistic conditions. Many engineering schools now operate dedicated living building laboratories, where algae façades, bioreceptive concrete, and adaptive envelopes are evaluated over time. Experimental buildings on academic campuses often feature photosynthesizing façades, green roofs, and self-healing materials integrated into structural elements. These projects allow researchers to measure energy performance, material durability, and environmental impact in real time. Sensors embedded within walls and slabs collect data on crack formation, thermal behavior, humidity regulation, and biological activity data that is invaluable for civil engineers refining design models. Beyond universities, several demonstration buildings have been constructed by forward-thinking developers and municipalities. These structures test how living systems perform in occupied spaces such as offices and residential units. Initial results show reductions in energy demand, improved indoor air quality, and lower maintenance requirements. Infrastructure pilots are also emerging. Bioreceptive concrete panels are being tested in pedestrian bridges, retaining walls, and noise barriers. These applications evaluate how living materials respond to weather exposure, load cycles, and long-term aging. While these pilot projects are often small in scale, their significance is enormous. They provide real-world evidence that living architecture can operate safely, efficiently, and predictably. Each successful pilot moves bio-integrated design closer to widespread adoption. Challenges and breakthroughs. Scaling bio-integrated architecture. While bio-integrated architecture has demonstrated impressive potential in pilot projects, scaling these systems for widespread adoption presents complex engineering, economic, and social challenges. One of the most significant barriers is engineering predictability. Traditional construction materials behave in well-defined ways under load, temperature, and time. Living systems, however, are dynamic and responsive, introducing variables that engineers must carefully manage. Ensuring consistent performance across different climates, building sizes, and usage patterns requires extensive modeling, monitoring, and long-term testing. Another major challenge lies in standardization and codes. Most building regulations were developed for inert materials such as concrete, steel, and masonry. Bio-integrated materials, especially those involving living organisms, do not fit neatly into existing classifications. As a result, engineers often face regulatory uncertainty, requiring special approvals or experimental permits that slow project timelines. Cost remains a critical concern. Early bio-integrated systems involve higher upfront investments due to research, specialized fabrication, sensor integration, and skilled labor. Developers may hesitate to adopt unfamiliar technologies without proven financial returns. Additionally, maintenance protocols for living systems are still evolving, requiring new expertise and training. Public perception also influences adoption. Occupants may initially resist the idea of bacteria, algae, or fungi being integrated into their buildings. Concerns about hygiene, durability, and safety must be addressed through education, transparent performance data, and clear engineering controls. Despite these challenges, breakthroughs are accelerating adoption. Advances in computational simulation allow engineers to predict biological behavior under structural and environmental stress. Automated monitoring systems ensure living components remain within safe operational limits. Costs are decreasing as materials move from laboratory to commercial production. Each breakthrough reduces uncertainty, bringing bio-integrated architecture closer to becoming a reliable, scalable solution for future infrastructure. The economic and environmental impact. Beyond visual innovation, the long-term impact of bio-integrated architecture extends far beyond visual appeal or experimental novelty. When evaluated through the lens of life cycle engineering and infrastructure economics, living buildings demonstrate compelling advantages that justify their initial investment. Traditional buildings often incur significant costs over time due to repairs, energy consumption, and environmental degradation. Bio-integrated systems fundamentally change this equation. One of the most significant economic benefits is reduced maintenance and repair costs. Self-healing materials automatically address micro-damage before it escalates into major structural issues. For civil engineers responsible for bridges, tunnels, and public infrastructure, this translates into fewer inspections, less downtime, and extended service life. Over decades, these savings can outweigh higher initial construction costs. Energy efficiency also delivers long-term economic value. Photosynthesizing facades, adaptive skins, and bioresponsive envelopes reduce reliance on mechanical systems, lowering operational energy expenses. In large buildings and urban developments, this results in substantial cost savings while improving indoor environmental quality. From an environmental perspective, bio-integrated buildings actively contribute to ecosystem restoration. They sequester carbon, improve air quality, reduce urban heat island effects, and manage stormwater naturally. These benefits reduce the burden on municipal infrastructure and healthcare systems, creating indirect economic savings at the city scale. Moreover, cities that invest in regenerative infrastructure enhance their long-term resilience. As climate risks increase, buildings capable of adapting to extreme temperatures, pollution, and moisture become strategic assets. Insurance costs decrease, asset values rise, and communities become more sustainable. For civil engineers, the conclusion is clear. Bio-integrated architecture is not merely an environmental statement. It is a financially and environmentally sound infrastructure strategy that delivers measurable returns throughout a building's life cycle. The future is alive. What's next for our cities? For over a century, cities have been engineered as rigid, mechanical systems networks of roads, pipes, and buildings designed to control nature rather than cooperate with it. However, accelerating climate change, resource scarcity, and population growth are forcing a fundamental rethinking of how urban environments function. The future city is no longer imagined as a static collection of structures, but as a living, evolving system capable of adaptation, regeneration, and self-optimization. This transformation is driven by bio-integrated architecture and living infrastructure. In the coming decades, cities will operate more like ecosystems than machines. Buildings will actively regulate heat, moisture, and air quality. Infrastructure will respond dynamically to environmental stress. Instead of being endpoints of consumption, urban structures will become active processors of energy, carbon, and water. For civil engineers, this represents a profound shift in professional responsibility from designing isolated structures to shaping interconnected urban metabolisms. Technological convergence makes this vision achievable. Advances in biological materials, smart sensing, artificial intelligence, and robotics enable buildings to adapt in real time. Living facades can respond to pollution levels, adaptive envelopes can optimize thermal comfort, and bioresponsive materials can repair damage autonomously. Over time, cities will evolve rather than deteriorate. Most importantly, living cities redefine resilience. Instead of relying solely on redundancy and over-design, future infrastructure will use adaptation and regeneration as core design principles. This approach reduces long-term costs, enhances sustainability, and improves quality of life. The future of cities is not just smart, green, or efficient, it is alive. And civil engineers will be the architects of this living urban evolution. Vertical forests and urban ecosystems, cities as interconnected living organisms. Vertical forests represent a powerful symbol and functional reality of living cities. These structures integrate dense vegetation across building facades, balconies, and rooftops, transforming conventional high-rise buildings into vertical ecosystems. Unlike decorative greenery, vertical forests are engineered systems designed to deliver measurable environmental performance. From a civil engineering standpoint, designing vertical forests introduces new structural, geotechnical, and environmental challenges. Engineers must account for increased dead loads from soil, plants, and retained water, as well as variable live loads caused by wind acting on vegetation. Drainage systems must prevent water accumulation while ensuring sufficient moisture for plant health. Root containment and long-term durability are critical considerations. At the urban scale, vertical forests function as ecological connectors. When combined with green roofs, permeable pavements, and urban wetlands, they form continuous biological networks that support biodiversity within cities. Birds, insects, and microorganisms re-enter urban environments, restoring ecological balance that traditional construction erased. These systems also mitigate urban heat island effects by providing shading and cooling through evapotranspiration. Surface temperatures decrease, energy demand drops, and thermal comfort improves. For cities facing extreme heat events, this represents a vital climate adaptation strategy. As vertical forests multiply, cities begin to behave like living organisms, regulating temperature, filtering air, and responding to stress. Buildings become the cells of an urban body, interconnected and mutually supportive. This is not architectural symbolism, it is ecological engineering at city scale. Policy and regulation preparing for a living built environment. The transition to bio-integrated cities cannot occur without significant evolution in policy, regulation, and governance. Current building codes were developed for inert materials and predictable systems, leaving little flexibility for living components that grow, respond, and change over time. As a result, regulatory adaptation is one of the most critical challenges and opportunities of this paradigm shift. Governments around the world are beginning to adopt performance-based regulatory frameworks. Instead of prescribing specific materials, these codes evaluate buildings based on outcomes such as safety, durability, energy efficiency, and environmental impact. This allows engineers to demonstrate compliance using innovative bio-integrated systems. Public funding plays a crucial role. Many governments now support pilot projects, research grants, and demonstration buildings that test living technologies under real conditions. These projects generate performance data that informs future regulations and builds public confidence. Professional bodies and engineering institutions are also updating standards and curricula to include bioresponsive materials, adaptive systems, and life cycle-based design. Engineers are increasingly involved in policy development, translating complex technical realities into workable regulatory language. As regulations evolve, bio-integrated architecture will move from experimental status to accepted engineering practice, unlocking large-scale implementation while maintaining safety and reliability. Role in the shift: how living cities will change daily life. The emergence of living cities will reshape everyday life in profound but practical ways. For residents, bio-integrated buildings will offer cleaner air, improved thermal comfort, reduced noise pollution, and closer connections to nature even in dense urban environments. Homes will adapt to weather conditions, offices will regulate air quality naturally, and public spaces will feel healthier and more resilient. For civil engineers and students, this shift represents a transformation of professional identity. Future engineers will not only design structures, but also manage biological systems, interpret sensor data, and collaborate across disciplines. Skills in sustainability, systems thinking, and interdisciplinary coordination will become as essential as structural analysis. Cities will become safer and more resilient. Adaptive infrastructure will respond to heat waves, floods, and pollution events in real time. Living materials will reduce maintenance disruptions and extend service life. Over time, infrastructure will improve rather than degrade. As citizens, people will live in cities that feel responsive and humane cities that support physical and mental well-being. The living city is not a distant vision. It is a gradual evolution already underway. The future is not about abandoning engineering principles, it is about expanding them to include life itself. As we stand at the edge of a new engineering era, one truth becomes clear: the future of construction is no longer inert, it is alive. Living buildings and bio-integrated infrastructure are not distant concepts. They are the next logical evolution of civil engineering. As engineers, students, and innovators, we carry the responsibility to design structures that do more than stand. They must adapt, regenerate, and heal the planet. At Civil Engineering Edge, our mission is to prepare you for this future by bridging theory, technology, and real-world application. The cities of tomorrow will be shaped by those who dare to rethink materials, systems, and sustainability. If you're ready to be part of that transformation, stay curious, stay informed, and stay connected. This is where engineering meets life and where the future begins.